Hello, Crina. Welcome to the first one of a series of podcasts by FYLA. We're delighted to start this series with a prominent scientist like you in nonlinear optics. And to start with, it will be great if you could please give us a brief introduction about your university and your research group.
Thank you very much, Sarah, and FYLA in general for the invitation. As you said, I'm Crina. I'm professor in the physics department of the Polytechnical University of Catalunya. And at research level, I belong to the nonlinear dynamics, nonlinear optics, and lasers group. Within this group that has a quite broad research activity, together with my colleague Jose Trull, we are responsible of the Laboratory of Nonlinear Optics. And we share our research that is mainly experimental with simulations and theoretical models that are able to evaluate our experiments.
And could you give us some insights about your research and the different areas that you work in?
We have several parallel research lines, but in general, we are interested from one side in the optical properties of periodic materials. These are artificial materials where the periodicity at micrometric or nanometric scale modifies and improves the interaction between light and matter. So during the years, we have worked with photonic crystals, with gratins, nanowires, and so on. From one side, we are studying the linear properties of these materials. And once we know them, we design them in such a way that the nonlinear interaction between light and matter is enhanced.
And what are the main interests and applications of these materials that you develop?
One of the main applications is the enhancement of second and third harmonic generation as nonlinear processes, together with the localization of the light inside of this structure that might bring to the nonlinear phenomena enhancement or to absorption enhancement. As applications, we can design any device based on second or third harmonic generation, as for example, an autocorrelator for the measurement of ultra-short pulses. We have worked for quite a lot of time in this direction. We can design active materials for photonic circuits. We can design sensors, for example. We can also modify or filter out the spatial profile of a laser beam, as for example, the laser beam coming from a semiconductor laser. Just to give few examples.
And have you actually ever transferred any of these results into industry?
Yes, even if our research is mainly basic research and we are interested in studying the physical physical meaning of the effects we are studying, of course, once we understand the basics, we think in applications. And during the last year, we have transferred to the industry an application, as I said, related to the ultra-short pulse measurement and characterization, a device, an autocorrelation device that we have patented actually. And also we have worked with companies in an European project to improve the spatial profile of semiconductor lasers.
For all these experiments, you use lasers as the illumination source. Which kind of lasers do you use?
For nonlinear optics, we need short pulse lasers of picoseconds or femtoseconds, usually centered of a particular wavelength. From this point of view, we are using lasers around 164 nanometers and also titanium sapphire tunable laser around 800 nanometers in the femtosecond range. However, before the nonlinear measurements, we need to characterize our sample. So for that, we need either an OPO that is able to give us a tunable range between visible up to near infrared, or even better, supercontinuum laser that offer the whole spectra at once.
So in your laboratory, I've seen you've got a supercontinuum laser from FYLA, the FYLA SCT. What do you use this particular laser for?
We use the laser to record spectra of the periodic structure in reflection and transmission as a function of the polarization, for example. With this spectra, we are able to know exactly where, at which wavelength, and with which optical properties we have to act in order to induce the nonlinear effects.
So what are the advantages of using this laser compared to other technologies available in the market?
Well, in the past, we used to do these measurements with an OPO. We have, together with a titanium sapphire tunable laser, this OPO was able to give us wavelengths between 500 nanometers and 1.3 microns. But in that case, we had to do the measurements one by one at each wavelength and then plug everything together. Of course, making the measurements with a supercontinuum laser, it's much better. First of all, because the spectra it's flat, it has a very good quality, and then we save a lot of time because we have the whole spectra at once.
So after this linear characterization of the materials that you work with, what do you use to study the actual nonlinear effects of the optical samples?
To induce second and third harmonic generation, we need short pulse lasers. We use two of this kind of laser. One is also a FYLA PS50, delivering pulses in the range of few picoseconds. And then we have a tunable titanium sapphire laser where we can make the measurements around 800 nanometers.
Could you tell us about your most recent project and what are your plans for the future?
In our recent project, we are trying to understand all the details of the light and matter interaction at nanoscale. Second and third harmonic generation are currently measured from different nanostructures, but not always people understand very well which are the different contributions to the nonlinearity. The models we usually use have approximation that do not stand at nanoscale. We did very interesting measurements with semiconductors, metals, or conductive oxides, which are strategic materials for nanophotonics nowadays, and we proved that there are some terms into the model that have a very important contribution to the nonlinear response. Once we understood what happened in homogeneous nanolayers, we are now moving towards nanostructures, periodic gratins, nanowires, nanoantennas, or other kind of real structure that can be implemented in photonic devices.
This is fascinating research. Thank you very much, Crina, for your clear explanation. We hope we can keep collaborating in the future as we've been doing in the past few years. Thank you.
Thank you very much.